All right, guys, Mr. Antonucci here, and we're moving on to the second part of significance tests for the slope of a population regression line. And we're going to talk about calculating the standardized test statistic and p-value for the test here. Now, if the conditions are met, we suppose the conditions have to be met for this to be able to work. We want to perform a test so we compute the standardized test statistic t, which is b minus beta divided by the standard error of beta. So then we find the p-value by calculating the probability of getting a test statistic this large or larger in the direction specified by the alternative hypothesis using a t-distribution with n minus 2 degrees of freedom. Now, again, as with other significance tests, the specific formula for a test about a population slope is not going to be on your formula sheet. But the general formula for test statistic and standard error of the sample slope are. So remember, the standardized test statistic is always the statistic minus the parameter divided by the standard error of the statistic. And then, so this formula will be on the formula sheet, and so will the standard error for test about a population slope. You just have to know how to put them together in order to get your t statistic and how to use that to then calculate your p-value. So here's an example. This is the foot problem from the last video, and we want to use the data to perform the test. So if we assume the conditions are met and we want to calculate the test statistic and p-value. So t, we're going to do the statistic, which is the slope from the computer output for foot length. So 2.7469 minus the null slope, the null for beta, which we assumed was 0, divided by the standard error of the statistic, which is this 0.7833. Okay, you get 3.507. And then we calculate the degrees of freedom, which is going to be the sample size, 15, minus 2, which is 13. And then if we do a t cumulative density function on the calculator with the t statistic, upper bound is 1,000, and then the degrees of freedom, you get 0.0019. So if we look at our distribution here, this is what we're talking about. This is a t distribution with 13 degrees of freedom. Our t value is 3.507, and so we're getting the probability of that value or more, which is 0.0019, which is a little less than 0.2%. Had you used table B, you would have got something between 0.001 and 0.0025. So if we want to interpret that p-value, remember, when we interpret the p-value, it's always in context of the problem where we assume the null is true. So assuming there is no association between x equals foot length and y equals height in the population of high school students, there is a 0.0019 probability of getting a sample slope of 2.7469 or greater by chance alone. So that begs the question, if we're doing a hypothesis test, what conclusion would we make? Well, because the p-value, 0.0019, is less than our significance level of 0.05, we reject the null. Then we need to state our conclusion. These data provide convincing evidence that the slope, beta, of the population regression line is greater than 0. So we have convincing evidence of a positive linear association between foot length in centimeters and height in centimeters in the population of high school students. So as before, the confidence interval, which we talked about in the last section, that will provide more information than a significance test. If we went ahead and constructed a 95% confidence interval for this context, it would be 1.005 to 4.439. Additionally, because all of those values are positive, the confidence interval gives the same conclusion as the test. We have convincing evidence that the association is positive. Plus, it also gives us an interval of plausible values for the slope. All right, guys, that's it for this video. Hope that was helpful. As always, reach out if you have any questions.